Welcome. Let's do question number 4. Part A, in regard to a typical convolutional neural network for image classification, answer the following questions with reasons. In what part of the network are the most of the learnable parameters? Part 2, what part of the network is most heavy in computations? So, dense layers in latter part is the answer to the first question. Yes. For this, the answer would be convolutional layers in the early part. So when we do part 4 of the question, you will understand this more. Okay. Part B, convolutional neural networks and other image processing systems sometimes need an image to be upscaled. So we are considering about taking an image and producing a zoomed in version of the image. An image and a grid are shown in figure Q4b. This image is to be scaled up by a factor of 1.5 using binary interpolation to generate a 12 by 12 image. Compute the pixel value at location 910 of the upscaled image. So you can see the scaling factor is 1.5. Okay, so in this image, we are concerned about pixel 910. So 910 would have landed in the original image at 901.5 and 1001.5 pixel the scaling factor, because this has been scaled by 1.5. So this is equal to 6, and this number is equal to 6.667. So therefore we have to see 0, 1, 2, 3, 4, 5, 6. So we are looking at this row. So although by linear interpolation, it becomes linear interpolation. And 6, 6, 6, 7. So therefore we need 0, 1, 2, 3, 4, 5, 6. This pixel and the rounded up pixel 7. This pixel. Yes. So let's draw this here. 58 and 83. So in between we are supposed to find, now if this is 6 and this is 7, we want to find 6.667. So you can see this is 2/3 and this is 1/3. 0.667 is equal to 2/3. So therefore value here would be 58 times 1/3 plus 83 times 2/3, which is 74.66, and the answer is 75. Okay, let's look at the question part number C. If 50,000 images of scale size 32 by 32 by 3 color, example C10 are available for training, and linear classification is to be done using vectorized images themselves, we should describe the procedure for training such a classifier. So what we need to do in this case is to, first of all, to generate a classifier. First of all, we need to define a loss function. For example, sum of squared loss, a scoring function, wx plus b, and find w and b through gradient descent, right? So the answer to that question would be define a loss function. Example, sum of squared loss. Define the scoring function. So this is a linear classifier. Fx would be equal to wx plus b. W is a weight matrix, x is the image, and b is the bias vector. And find W and B using gradient descent. Part 2, what would be the weights of each classifier look like when seen as images? If you take this W would be of size. Now 32 times 32 by 3 is 3072. And there are 10 classes. So W would be 10 times 3072. And B would be of a 10 vector. Now, if you take each row of W, take a row of W, that will have 3072 numbers, and we reshape it to an image of size 32 by 32 by 33. 3 because it's color. So they will look like a blurred version of the class. So example, car. So it will look like a blurred version of a car for the if this is the car class. If it is a ship class, a blurred version of the ship. Then let's do part 3. Consider this data set of 3 classes. So therefore you can see W has 3 rows. So dogs, cats, and bunnies. As image is represented by a 5-dimensional vector, a linear classifier after learning process is represented by this one. So you can see B has 3 numbers to account for the 3 classes. The first row of W and B is the 1 versus all classifier for dogs, the second for cats, and the third for bunnies. Determine the class of the image with feature vector x equals 1.3 minus 1.2, 0.8, 3.1, 2.0. So what you have to do here is take W and write vector x beside this. 1.3 minus 1.2, 0.8, 3.1, and 2.0, and then add B 0.2, 2.2, 3.2. So what you would do is you would take this row, multiply with the image column, and add 0.2 to that. So therefore you will get 3 numbers corresponding to the 3 classes: a dog score, cat score, and bunny score. So what you would get here would be, if you do the calculation, 1.2 minus 0.53 and 3.24. 3.24. So you can see this number is much larger. So therefore it will correspond to bunny glass. Okay, part D, consider a neural network implementation for digit recognition. There are 10 digits from 0 to 9. Assume that each digit is 32 by 32 grayscale image. The network flattens the input first. There are two dense layers, one connecting to 100 nodes and the other connecting to 20 nodes. These 20 nodes are connected to the output. Now, how many nodes must be there in the output? There are 10 digits, so therefore 10 classes, so 10 nodes. Sketch the network. So 32 by 32 is 784. So 1 and 784 nodes. And then these are connected to 100. This is the 100th node. So these are densely connected. That means each node here is connected to each of these. Like so. Then there are 20 nodes. These are also densely connected. And then there are 10 output nodes. These are also densely connected. That's the network sketch. Compute the number of learnable parameters in the network. So in this layer, 784 times 100 connections plus 100 is the bias. For this one, 100 times 20 plus 20 is the bias. In this one, 20 times 10 plus 10 is the bias. So how much would you get there? by 32 is 1024, right? So this one is 102,500 plus 2020 plus 210 altogether 104,730 parameters. So you can see these are dense layers. So you can see the number of parameters is quite large. But if you take a convolutional layer, let's consider, for example, a convolutional layer. Now this is 32 by 32 image. If we its depth is 1, if you consider convolution kernel of, let's say, so 3 by 3 by 1 convolutional kernel. So you can see, let's say there are 64 such kernels. So how many learnable parameters are there in this convolutional layer? 3 by 3 for each times 1, because depth is 1. And there are 64 of them, 64 plus 64 biases. So this is, you can see the number of learnable parameters is small. Here the number of learnable parameters in each layer, if you take, is large, right? But here the computations, the number of computations that we have to do is high, because we have to place this kernel at every single location of the image and carry out 3 by 3 multiplications and 8 additions. You can say 3 by 3 multiplications and additions. So that's why for this one, we wrote that most learnable parameters are in the dense layers, and the computational heavy part is in the convolutional layer. Okay, that's the answer to that question. Thank you.